Good evening and a very warm welcome to the black hole. We often take numbers for granted, assuming they are simply a fundamental aspect of our lives. हमने पहाड़ों से नंबरों को सीखना शुरू किया एक दूनी दूनी दो दूनी चार and चल सो चल. However, the truth is that numbers have been the subject of intense academic, intellectual, and philosophical debates for centuries. For instance, the number 3 in isolation holds little to no meaning, but 3 idiots suddenly give it tangible significance. यानी कोई यूनिट या कोई डेफिनेशन तो होना उसके साथ. But what about negative numbers? Their physical interpretation has long been a topic of discussion among mathematicians and philosophers alike. ये आज की हमारी गुफ्तगू का थोड़ा सा पस मंज़र है. गुफ्तगू का उन्वान आप मेरी बैग पे बोर्ड पे लिखा हुआ देख सकते हैं. From sets to multisets, a new perspective on numbers. वो नया perspective क्या है, नई तोजी, नई interpretation क्या है. I am as curious as all of you. और इसके ऊपर गुफ्तगू करेंगे. मेरे दाएं जानिब तशरीफ़ फरमा है डॉक्टर मुख्तार उल्लाह. He is the Dean of Engineering at FAST, National University of Computer and Emerging Sciences. He holds a master's degree in Control Engineering from the University of Manchester, Institute of Science and Technology, UK, and doctorate in Computer Science from the University of Rostock, Germany. आप इससे पहले भी इसी तरह के मौज़ूआत पे कुछ लेक्चर्स दे चुके हैं जो आप हमारी वेबसाइट या यूट्यूब चैनल पे इस गुफ्तगू के पस मंज़र को समझने के लिए ज़रूर देख लीजिएगा. आप सब लोगों की आमद को शुक्रिया. प्लीज़ अपने सेल फोन जो है वो साइलेंट मोड में कर लें सो दैट देयर इज़ नो डिस्ट्रैक्शन. आप भी गुफ्तगू में शरीक होइएगा. जस्ट रेज योर हैंड फर्स्ट ताकि आपको जो माइक्रोफोन दे दिया जाए और फिर आपकी आवाज़ जो है वो रिकॉर्डिंग में भी आए और ऑनलाइन ऑडियंस तक भी पहुँचे. नाउ प्लीज़ वेलकम डॉक्टर मुख्तार उल्लाह. थैंक यू.
Assalamu alaikum, everyone. I have been given lectures on similar topics in the past. Because this idea is related to one of my earlier lectures where I used the idea of sets to define numbers. So in my first part of this lecture, I will try to actually review that part. It will not be lengthy, but I hope you get the main idea. If you want to actually go to depth for that, you can watch that lecture. Yeah. Magnitude, multitude, and numbers, something like that. So let's go to let's say grade 2 or grade 1, yeah, where kids are exposed to counting. So, and you can also recall as a child how you were counting. So if you want to count, although you use numbers, like 1, 2, 3, but you always like to associate those names or numbers to something physical. So sometimes you use fingers, sometimes you draw things, yeah? Like the best way I remember was if I want to say 3, so I can simply draw 3 lines, yeah? 3. And then I can say, okay, what if I want to add 3 and 2? So what will I do? Like, yeah, 2 more lines, yeah? And now I have 5. So this is an illustration of 3 plus 2, and I can use fingers as well. Now, later on, and when you go to higher classes, like 6th or 7th, then things become more sophisticated, and then, okay, then you try to, because this is a very basic way, yeah? This doesn't look very mathematical. So then you are exposed to sets, yeah? So instead of drawing these lines or instead of using your fingers, okay, you can say, okay, I have a collection of objects called a set, and everyone is aware of sets. But we never question that this connection is immediately lost the moment you define set. Because if all these lines are identical, then it will not qualify as a set, because in a set, repetition is not allowed. Yeah. So if I have this as one set, and if I have this as another set, this will have one element, because I'm not supposed to distinguish, and this will be another element. Similarly, even if they are different, there is still a problem. Okay. You say, okay, I'll not use. Some people do a trick here. that even if I have three identical fingers or two identical chairs, yeah, I can label them in my mind, yeah, the first one. So I can say, because I'm calling it the first line, the second line, the third line, even if they are identical, in my mind they are different, right? So that is a mathematical trick that is not very great, but mathematicians try to actually defend their set theory by labeling. Yeah, I'm labeling it in my mind. So even that is a problem, let me tell you. Let's say I label them and let's say, call them, okay, bar 1, yeah, bar 2, and bar 3, okay? And forgive me for using these 1, 2, 3 because these are also numbers, but maybe you can come up with some other symbol, yeah? A, B, and C. Okay, so now I got around that issue of repetition. So let's say I do the same here, yeah? Now I have two sets where the repetition problem is gone. Now let's add the two. 3 plus 2. You still have a problem. Sorry. Because when you are taking the union, of course you will use union for addition. So what is the union of these two sets? Yeah, so you don't get 5. So that's the real problem. Okay, so this problem exists and we're somehow trying to hide this behind the rug. Now, how mathematicians have solved this, I'll just briefly say how they got around that problem. So what they do, and actually this was one of my lectures, that they say, okay, these are physical things, so just we don't talk about them. So the numbers are associated with sets in such a way that none of this problem actually, okay, this union will still be a problem, okay? But to get around these problems, what you can do, okay, let's say I have an empty set. You remember measurements, yeah? Like when you are, let's say if I want to say that this is, how much do you think can this length be? Just guess. 3 to 4 centimeters. So if you want to be exact, you will compare it with an actual, yeah, scale where it's a label. So you can see that as a template to match. And then you can say, okay, what is the most precise way of doing it? So maybe you have some sample in Paris, or maybe there are some physical experiment, things like that. So similarly, instead of saying 2 fingers, 3 apples, yeah, 4 markers, these are physical things. So you need a template on which everyone agrees. So for that, I can use sets. So I can use empty sets for 0. Yeah, this is that pure template. Yeah, and I can use remember, I have created 0 from nothing. Yeah, now this is a set with 0, and that 0 itself is nothing. But the math helps me define the number 1, again from nothing. Now, this from nothing is there to have a universal template where everyone agrees what a 1 should mean. So regardless of whether you are using a marker or a finger or whatever you do, you have that abstract, pure, clean template with which anything. So if 2 people are actually arguing about whether it's a 1 or a 2, you can say, okay, map it with this, and it's a 1, it's not a 2. So can you guess what will be a mathematical way of creating 2 then? Just from these 2?
Bracket in one.
Yeah, yeah, bracket 1, 0 and 1. So this is 2. Okay. So, and this is really clever, okay? Because if you now want to add, yeah, you can use this for addition, and because the way these sets are defined, that overlap is also avoided, things like that. But the problem is that, do you think how many students are exposed to this trick? Very few, yeah? Because when we say sets, we give examples of sofa set of chairs, set of people. Yeah. So of course people are different, but chairs can be identical. Yeah. So if I now open two boxes or two bags, if you can see it, I can use this this pouch as a collection. Yeah. So you should not care what this itself is. This just serves the purpose of collection. But these three are different. Okay. Although the color is the same, but they are different sharpeners. So if I now use this one, yeah, they're all the same. Yeah. Of course, you can. Okay, maybe some label is different, but how about these ones? Yeah, these three chalks, they're all the same. Yeah. So the issue is everybody is exposed to collections where items can be identical. Yeah. And just look about the spelling of your name. Yeah. If your name has an A appearing two times, that A and that A is literally the same. You cannot say I will say it's the first A and it's the second A. I mean, it's just cheating. Okay. So things will repeat. Yeah. So we need a collection of objects which is different from sets, because sets have this problem. Yeah. So if you want to make this exercise of counting more sophisticated at the school level, the first mathematical object to help that, let's say in grade 5 and grade 6, I'll still agree with the idea of using those bars and fingers and markers, because kids till grade 5 or grade 4 are too actually naive to appreciate more complicated concepts. But in grade 6 or 5, they should be exposed to the mathematical object of a bag. You can call it a bag, you can call it a box. Yeah. A more mathematical name is multiset. Yeah. So the multi is reminds you that things can be repeated. But there is one thing which is common in sets and multisets, that the only difference is that in sets objects are not allowed to repeat, and in multiset they are allowed to repeat. But there are two things which are common. The order doesn't matter. So it doesn't matter which one appears first. Yeah. So if I put this one here and this 0 there, it will still be the same set.
Order doesn't matter.
Order doesn't.
Both the cases.
In both the cases, yeah. That's why I told you the only difference between a set and a multiset is the repetition. And you must be wondering, what will be a name for a mathematical object where order also matters? Yeah. Of course, we would not call it a collection, because the collection as we use in day-to-day language seems not to care about order. Yeah. So, but you are using it. I mean, I would not be too strict. Maybe you have collections where order matters. For example, the batting order. Yeah, I can send, let's say, 16 players to on a foreign trip. Yeah, just like the Pakistani cricket team is now playing. How many players do you have to send for an event? 16. Yeah. So that 16 is a collection which is unordered, because you only have to know who is going and who is not going. That's the only thing that matters. But on a particular day, even then, which 11 will be playing, the playing 11 is also unordered. But the batting order, who will be the opener, that is then an ordered collection. So a better name for that is a list. Yeah, list. So when you say list or array, maybe the computer scientists, they like this word array. Maybe in school, in assembly line, yeah, you can say, okay, this student will be standing here, 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 here. Or in functions, yeah, you reserve certain seats for certain people. So, but let's not get into the order here, okay? So, unordered collection of objects, which some of them may be identical, is what is called a multiset. Yeah. For short, we will call it Msets. But you can think of it as a bag. Actually, the computer scientists, they use the word bag. For those of you who have heard something about language, natural language processing, NLP, it's a very popular field in computer science these days, and data science to be precise. They use a model which is called bag of words model. Yeah, let me just write it down. Bag of So now I'm going from the basic to a very sophisticated concept, okay? So what they do, let's say they want to classify a document, yeah, automatically. You read a document and you want to know whether it's of this type or of that type, or, yeah, or whether it's a song, or yeah, whether it's a good movie or a bad movie, some description about anything, yeah? A comment, a Twitter comment, whether it's against the government or it's in favor of the government, all these kinds of automatic, yeah, classifications. So what they will do in that document, they will only try to collect how many times a particular word has appeared. Yeah. So if the word, let's say, yeah, we could say C B B B, yeah, here. Yeah, here one appears, but the basic symbols I'm using to write any number, it comes from that. So that is now a set. Yeah. So you need set if the collection is of types. Yeah. So if I now, how will all these chairs suddenly become? Let's say here I'm talking about different types of seating arrangements. You have chairs and you have sofas. So in this hall, and how would you classify this one? Couch, yeah. So there are actually, I would say, 3 types of things. Yeah, these chairs, yeah, 4 types. Yeah, 4 types. Yeah. So I will say the common chair and the special chair and the sofa, and I can actually, I will say vanilla chair, yeah, and special chair and sofa, yeah.
Floor.
Yeah, so you can sit on the floor as well. So these are situations where you do not want, because mathematics is about simplifications, yeah. Unnecessary details must be thrown away. So whenever the details, so for example, if I say letters, then I don't care how many times do I have 0. 0 is a 0. Yeah, chair is a chair. I don't care whether there are 50 chairs or 10 chairs. So in a problem, it might be the case that the exact number is actually not important, and it only spoils your analysis. It actually makes your job difficult. So in those cases, what the mathematicians do, they actually throw away unnecessary details, and that is the idea behind a set. But not always. In counting, just as I gave the example, it matters. If I'm counting chairs, I should care about all these chairs, even if they are identical. So I cannot use set here. I must use multiset. And now you must be wondering, okay, why should I care? Okay, I have been counting my whole life, and I never used multiset. The idea is basically is that when we are using these numbers, basically 2, 3, 4, you need a very crisp concept of what is that object. So that's now a foundational question, okay? So now, remember, why did we write that thing and that thing, yeah? This was needed, although it was using sets, this was needed so that you have a precise way of what is a number. So if I ask you what is 2, and if you tell me 2 apples, no, you're not telling me 2, you're telling me 2 apples. You're corrupting it. What if there were no apples in this world? Then you would say 2 chairs. So what if everything actually is just destroyed? All the civilization disappears, and you only have empty space. Do you think 2 will lose its meaning? No, 2 will still be there. Because information, so there are actually 3 things if you want to build a house or you want to cook something in kitchen, okay? 3 things are needed. Matter, because you need ingredients, yeah? Energy is needed to rearrange them, yeah? Only then you get something, yeah? But we miss out the third one, information. I can give you all the energy in this world, I can give you all the material, but if you don't know how to do it, you will never be able to make anything. But we forget that information itself is neither matter nor energy. Information is this. Information can be created from nothing. Literally nothing. And it actually resonates with the latest theory about universe, is that this universe was created from nothing. So just to have a short overview of that, matter and energy, do not say matter and energy, because matter is actually energy. Yeah, it's just a name we give. When energy is confined to a narrow region, we call it matter, but actually it's energy. Yeah, so the meaning of this equation, you must have heard this equation, yeah? Yes? Yeah. The most actually disturbing way of interpreting this is that, oh, mass is converted to energy. No, there is no conversion. This is actually telling you, this is actually the definition of mass. Just like if you have 10 billion rupees, maybe a better way is to report that amount in dollars, because that number will be small then. Yeah? But only to compress the information. Or maybe it's a better way is to report that in terms of gold. Yeah? But you're not converting, you don't have a factory which processes the paper and turns it into gold. No, that's not what is meant by conversions there. The conversions are actually the equivalents. So what is meant by this equation is that if you have energy limited, confined to a region of space, maybe that is a large number into one place. So actually this equation should be written like this. I find this more appealing, because this tells me how to report that as a smaller number, because this denominator is very large. Yeah? And this c, speed of light, doesn't mean, many people think that mass has to move with the speed of light in order to become energy. Mass cannot move with the speed of light, sorry. This c appears only as a coincidence. Nothing is moving. Yeah. So coming back to that earlier question, what you have is only energy. Yeah. Matter is just a name we give to energy. So when the energy is free, photons, you confine it, because the constituent particles in an atom, quarks, yeah, there are actually photons, but they have been actually trapped. When you trap them, you call it matter. So matter and energy, so let's use the word energy. Now that energy in the latest model has 2 forms. One is positive energy and one is, and it has nothing to do with philosophy or Sufism or religion, okay? Positive energy is the energy needed to expand, like dark energy, you must have heard it, yeah? This universe is expanding. That requires positive energy. But it is not blowing up. Things are still in place, yeah? So the energy needed to hold it, the gravity, that is called negative energy. And in the latest cosmological model, the total energy, because these are 2 types of energy, is 0. So it means that you can start from literally 0 energy, but if you have information, you can create this universe. So, why did we start this discussion? Okay, yeah. So the idea was about numbers. Okay, so when we say numbers 2, 1, 3, we need a concept that does not require physical objects. Yeah. So, for example, physical object should be requiring that object. So 0, 1, 2, 3. These numbers are pure, they are abstract, they are powerful. So they should be required by the physical object. The definition should not require the physical object. Only then they are worth the glory and the respect. If the definition of 2 requires markers, then it's not pure, then it's not powerful, because then I will need markers. And a civilization which does not have markers, okay, they will not be able to take advantage of that. So just to motivate this discussion, when you have a transaction from one person to another, from one bank to another, or using your Easy Paisa, what is being transmitted? Zeros and ones. Digital communication. It's a string of zeros and ones. These zeros and ones don't require that money. They don't even require. Yeah. So the theory should not require the physical things. Yeah. So now I think it should be very clear that if mathematics is to rule the world, and if mathematics is to rule every other subject, it itself must be definable as an abstract thing. Yeah. So now those numbers, coming back to numbers should be defined in terms of mathematical objects. So you should be able to tell what is 2, what is 1, what is 0, what is 3. So you cannot just say counting, because you are counting something. And that something then takes you back to the real world. Okay? And in a computer program, you're writing a computer program, you're just writing code, yeah? That code you can run that on a Windows machine, you can run that on a calculator, you can use hand calculations. Yeah, so now it means that in grade 6 or 5 or 7, it depends on the policymakers, that set should be replaced with multisets. This is my actually request. So that the definition of number, yeah, is given. Now I mean that advanced definition, yeah, should be given in terms of multisets. And why this matters? Because number one, kids will have a very clear and crisp and clean understanding of numbers. They will know what they are, yeah, and they will apply it to the physical world, but the physical world will not be needed. Okay. The advantage of this abstract nature is that you can apply it to anything. You don't care whether you are counting things, whether you are counting, stories, yeah, whether you are counting words, yeah, anything. So now we will build these numbers from the multisets.
Sir, a question.
Uh-huh.
That you said this should be replaced with the multiset.
No, I don't want to say that set should be replaced with the multiset. Set must be taught in its own right.
Yes.
But not to define number.
Okay.
Yeah.
Right.
Numbers should be defined in terms of multisets. Similarly, once we define, now I'm giving you an advanced view of what is coming up next. Once you replace, so I'm replacing these sets for defining the numbers. Sets are useful in their own right for other things. I'm not denying that. But because they have these problems, that when you use sets to define numbers, you are then handicapped, then you cannot use those sets for addition. You cannot use those sets for subtraction. You cannot use those sets for multiplication. So it should be a coherent picture where the building blocks are there for every new operation you want to define. And multiset is the right object for that. So it is not only the right object for the future definitions, but it is very, I would say, it is relatable to the real world. Yeah? Immediately, every student, every child can relate a multiset to some collection, a bag. Yeah, I mean, the moment you see this pouch, everything is so clear. It's a collection. It's a collection of things. So, so now we need some notation.
So,
Yeah.
sir, question.
Uh,
The other principles which we use in sets, like
Yeah.
union, intersection,
that is intact.
that will be applied on multisets also or not?
No, we need a new language. Yeah? You need a new language. So, for example, when you are taking the union of two sets, yeah, you're taking the union of two sets. That is not going to give you addition. We need something which facilitate our understanding of addition, of arithmetic, addition, multiplication, division, yeah, subtraction. Sets are not suitable for that. That's the idea.
Okay,
Yeah.
thank you.
आप ये कहना चाह रहे हैं कि जो हम
Yeah.
आप ये कहना चाह रहे हैं कि जो सेट है उसकी अपनी जगह वैल्यू है
बिल्कुल।
बट उसको डिफाइन करने से पहले हमें मल्टी सेट को डिफाइन करना चाहिए ताकि
Set और set
उसको
उसके
सेट
बाद
को
define
अंडरस्टैंड करने में इजी उनको
Yeah.
इजी
Set बाद में define करें।
और द सेम थिंग इज कि जैसे उन्होंने यूनियन और इंटरसेक्शन की बात की है इससे देन उनके लिए ये हो जाएगा कि मल्टी सेट्स को जब उनके माइंड में वो रखेंगे मल्टी सेट्स को देन दे कैन इजीली अंडरस्टैंड
Yeah.
व्हाट यूनियन इज एंड व्हाट इंटरसेक्शन इज अकॉर्डिंग टू दैट मल्टी सेट्स यू नो
Actually, understanding sets or defining sets will become much easier after this. Because you have understood something which is relatable to the real world,
Yes.
and a set is actually more sophisticated, it's more advanced, it's more abstract. So going from multisets to sets is very easy, it's natural. But going from sets to multisets is difficult because you have to unlearn many things.
यस
So the damage is already done, okay? So we want, actually, I only request to actually, to save the future generation from this damage. Yeah, give them these definitions in the right order so that they don't get confused, okay? So we should now agree, because I cannot have a pouch on this board, okay? And maybe sometimes it's not a pouch, sometimes it's a bag or a purse, a wallet, whatever. Yeah. So we need some symbolism here to denote a multiset. So just like we use these brackets, yeah, for sets, you can have some other notation for multisets, and that notation doesn't matter. Actually, there is no standard notation. Some people use, for example, this instead of that. But you can actually disagree with that. You can say that this is used, especially if you are a programmer, this is used for lists, and in lists, the order matters. If you have used Python, for example, yeah, or MATLAB or any other programming language, or even C, chances are high that you have used this notation, and that is used for arrays or lists. So mathematicians who don't care about programming, they are happy with this notation. But if you care, then there is another notation where they just write this thing double. Yeah? Double reminds you that things can be repeated. Yeah, multi. I don't like both of these because this is difficult to write down. This has a clash with programming. There is another notation which is very cool, and that actually reminds you of the bag. So, are you aware of Unicode? Unicode? Has anyone heard this name? Okay, then forget about it. Okay, it is a system of actually typing these symbols in a computer. Yeah, Unicode. So. Maybe,
Sir, this double bracket means multi-set representation.
Yeah. This is a possible notation. Yeah.
Okay, thank you.
So the one I like is this one. Look, this looks like a bag.
Integral and inverted.
Yeah, but this is that. Yeah. And actually, Unicode allows you to type that. I mean, if I had a computer right here, I could just type a command and this will appear. So this some people use this, but the majority use this. So because today we are not programming, so I will choose something which is easier. Yeah. on a board.
So, sir, multiset is one of the basic element in programming.
Yeah, they use it. Multiset. I told you bag of words model.
Okay.
Yeah, but of course it's used in advanced. They don't have a preferred notation. You need some data structure. So if you have used Python, you must have heard something called dictionary. Dictionary, yeah. In a dictionary, what they do, they use something like this, yeah. But instead of listing the numbers, so for example, instead of writing A, and A 3 times, and let's say B, and B 2 times, they would write A, and then they will write how many times it is going to repeat.
A3.
Yeah, that's the concept of dictionary. So you can simply say A, and maybe you can say 3. Now this 3 doesn't mean that A times A, but just repeating. You can use some other symbol. Some people just write a colon, yeah. I mean, I don't think this matters, yeah. It's up to your taste, okay. The main thing is the idea. The idea is that we need a notation. So we will not use these shortcuts, yeah. So let's agree on this notation, yeah. And when you are typing, you can choose some other notation. So, for example, here I can write A, B, A. Now this is a legitimate multiset. Okay. So if you want to convert them this into a set, it will become what?
AB.
Let's say I have a command called convert to set. It will become. So now you should see why this should be taught before set, because a set is just a special type of this.
Yes.
A set is a special multiset where you choose to ignore how many times an object is repeated because you don't care. ये जिस तरह हम कहते हैं ना कि एक दफा आपने ये हरकत कर दी मेरे साथ ना तो दोबारा बात नहीं होगी. I don't care how many times. आप 100 दफा करते हो या 1000 दफा करते हो. That one time is enough for me to stop terms with you. So I mean that could be one example. Yeah. So are we now clear about this? Do not actually be strict about this. You can come up with any other notation. You can read, yeah, and you can use a preferred notation. But we will use this for today's lecture. Okay. So now, how can we build these numbers? By using multisets, right? So, and because I already gave you that exposure to sets, so now you can actually participate in this exercise. So how should we define 0? If you remembered what I just did
Nothing.
a while ago. Yeah, nothing. Okay. Oh, yeah. Actually, it's very good that you said that word. Okay. So the reason this exercise is needed, I actually failed to remind you that. Okay. So it's not just the mathematical purity or cleanness or sophistication, but it's another realization. Okay. So for example, if I say, even if I'm using markers, let's say I say 3 markers. Okay. Now, so 3 is only the count, but when I say markers, I must have the real marker in my mind. Okay. So I must be able to distinguish between the count and the things I'm talking about. Yeah, right?
Right.
So this is very important because this happens in physics as well. In physics, let's say we typically say, or maybe I used to land, okay? So I say, I bought 30 square meter
Of land.
okay? I don't want to say land. I just say I bought 30 squared meter. Maybe we understand this, but this is technically wrong. Because what I wrote is a quantity attached to something physical. This is a property of that thing, but that thing itself is entirely different. That is a region of land, a piece of land. So I must be able to distinguish between the number or a quantity. This is not a number because this is a quantity. Yeah? A number with a unit is a quantity. Okay? This quantity is attached to a region or a plot or whatever you call it. Yeah. So this is another reason why we need to be able to tell what am I counting or what this number refers to. So when you say nothing, actually it reminds me. This actually I need to get into that. So when I write this thing, let's say I define this as 0. So we should be able to tell what this means. What this means is that 0 is a new definition which uses nothing. This is not nothing. This is nothing. The pouch is empty, yeah? The pouch is empty. But this is still a pouch. So nothing is not equal to an empty pouch. And this is very important in computer science because you need to be very strict about types. Yeah? This is one type, and this is another type. Although you are using nothing, but 0 is not nothing. 0 is the number of elements in nothing. It's a property of nothing. How many objects do I have in this pouch? No, 0. So 0 is a property of nothing. And even only when that nothing is actually seen as a collection. So this symbol reminds me that I am seeing a collection which is empty. So we should use nothing for this part, an empty collection for this part, and this is a convenient label because I don't want to draw this every time. Right?
So, sir, 0 is equivalent to nothing.
No, 0 is not equal to nothing. 0 is an object, yeah, which is a collection of nothing, an empty collection. Because this is a collection. If I remove this is not 0. Yeah. So I am now, and why do I need this? Because, yeah. So because this mathematical definition now helps me relate this to all the empty bags. So whether it's an empty pouch, whether it's an empty pocket, or whether it's an empty bank account, which I do have these days, they all are. Because why do we need measurements? Yeah, I just gave you an example of 2 centimeter, 3 centimeter. We need a pure template to which everything can be compared. So all the empty bags, all the empty rooms, all the empty pockets, they're all represented by this pure mathematical object. Yeah? Yes.
I'm sorry, मुझे ये इतनी सही समझ नहीं आई, but आप ये कहना चाह रहे हैं कि जो 0 है, it's just a representation?
No, it's a label. It's a name.
For this.
If you are happy to write this every time, then you don't need 0. Yeah. हम जब देखो ना, हम जब 2 करते थे, 2 हम किसको करते हैं?
0 and 1.
नहीं, वो रियल में आप ये कहते हैं ना, 2 markers, 2 markers. So it's just a notation. It's just a name you give to the number of collections. Okay. So you need some notation which is easy, which has been used. So this is, previously this was an empty set. Even there, you could have asked this question. Yeah, this is actually nothing, and this is an empty collection. So only when so actually it is a new mathematical object. You still create it out of nothing, but it's a different type. And why it matters? Let me tell you why it matters. Yeah. If I now, let's talk about this. Yeah. if I contain it in another collection, this is empty, but this is not empty. So I can now do something. I can put this empty back.
It's not equal to 0 now.
Now this is not empty anymore, okay? Yeah. And you can even do this in your mind. So because when you're doing pure math, everything is in your mind, but in a computer, it will be seen as a different type. And this is exactly what is happening in these programming languages. Yeah? Everything has a type. And if you have to be very specific and very strict about these types if you want to build your definitions. We will be building this, our definitions on these types. Okay. So if there is any confusion, you should ask it right now, because then it becomes very difficult later on. So we want to distinguish. Actually, there is a basic question. Okay, I should be asking before this. Okay. Let's go back to your sets. Yeah, and you have a set with 3 items. Yeah, A, B, C. And similarly here, I can put 3 different things there.
ठीक है.
These are 3 different pencils, right? So I'm not violating the definition of set. I'm putting them here, right? So now, in English language, I will call it a bag of pencils, yeah? A bag of pencils. Now, you please try to remember the question you asked before this lecture, yeah? 2 chairs, you said 2 chairs, yeah?
Okay.
So if I now remove this bag physically and mentally from my head, and I just take them out, now what is this? 3 pencils. But maybe I don't want to see this as a set anymore. So it will be very nice if we have a name for this as well. So when I say a collection of 3 pencils, I am automatically containing them in a container, even if that container is imaginary. It doesn't need to be physical, remember. I don't need physical pouches. But when I say a collection of 3 pencils, I see this as a set. So, because I have been actually reading about this and watching many wonderful videos, and I cannot give you all these references because they are very scattered. There is one computer scientist turned mathematician. Yeah? He was a computer scientist, but after his retirement, he started taking these questions very serious. And he proposed a name for these things. Things which are not contained. And the name is, I just love that name, bunch. It's a bunch of 3 pencils. Yeah. So if I remove this, it's a bunch of 3 letters. It's not a set, it's not a multiset.
When we will say it's a set, it means
Container.
collection of...
Collection, yeah, and by collection you mean the container.
Okay. And on the other side we say bunch.
A
when
bunch
it
means
is
it's just
without.
it's just a list, or I don't know. Bunch, yeah, don't say collection, just say bunch. The problem is that I have these 3 pencils. Actually, you decide, yeah? Because the pencils cannot tell on themselves whether they are to be seen as sets or not. So mathematics is about your language, okay? So whether you want to see this as a bunch or a set or a multiset, it's your choice. They cannot decide. So you see this. So mathematics is a language, yeah, and you have to decide. So, and this is very important, yeah, because if you fail to realize that you are the one who is doing everything, you are the one who is deciding what to, then you will not realize the importance of modeling. When we model something, let's say in physics you hear this name particle, yeah, particle.
Yes.
A particle has no size, 0 size. It has no color. Yeah, it can only have one thing, and that is the mass, or maybe it can have a charge. Yeah? Charge, for example. So, but the real thing, the real electron, the real proton, they do have size. They do have shapes. A particle is not supposed to have any shape either. So when you say a particle, it is your choice to model an electron as a particle. It has nothing to do with what the electron actually is. And we fail to realize this, right? That's why this problem of particle wave duality. Yeah, when you say wave, electron is a wave. It's again your choice. Electron is not going to tell you whether it's a wave or a particle. In some problems, you find it easy to see that electron as a particle because it helps your calculations. And other problems, like in photoelectric effect, when Einstein was explaining photoelectric effect, he saw light as photons, as particles. But the same light was viewed by Maxwell as waves, and both are correct. Why? Because they were dealing with different problems. So we should be very clear to distinguish between things as they are and things as we model them. And this is something which we forget every time. Yeah? We give names to things. The moment you give a name to something, you are actually modeling it. And it's very fundamental. Chair, okay? When I say you are sitting on a chair, this is already a model because I have decided to classify this object as a chair. Someone can make a table which will look like a chair by putting a strip. Let's say I turn this table, right? This is a table, yeah? Nobody will call this a chair, right? Mm-hmm. I can take a piece of wood and put it here, just a narrow piece, and you will start debating, oh, it's a table. Or I will say, no, it's a chair. Maybe it's neither a table nor a chair, but you have to decide whether you want to view it as a chair. So the problem is that the names we are using are models. And they're reasonable in some cases, unreasonable in other cases. The real world doesn't care what name you use. This chair doesn't care whether you're calling it a chair or not. So electron doesn't care whether you see it as a particle or as a wave. Maybe it's something yet to be discovered. So was that the question or was it something else? Okay. So yeah.
What if I say I need a pencil, or what if I say I need 3 pencils? So how are you going to put them in a set?
You need 3 pencils.
Yeah.
You just need 3 pencils. I'll give you 3 pencils. You didn't say whether you want to see this as a set or not.
Yeah.
Calling it a set is actually a choice where you model this as a set, because when you say a set, it means that you're not viewing this as a multiset, for example. You're not viewing this as a list. You're not viewing this as a matrix, for example. So that is a mathematical choice. We don't need those names if you just need pencils to write down, then you don't need to use the word set or multiset or a list.
So it's getting a little bit confused, like a pencil, bunch of pencils, or 3 pencils.
Bunch of pencil is actually, if we agree that a bunch of pencils does not suggest that I want to see this as a set or a collection. I do not want to contain it. Maybe that analogy can help. Have you heard in physics there is something called boundary? System and boundary. It's very important, okay? So let's say we are in this room, okay? So if I only want to talk about, what is your name? Sheroz, okay. So if I only want to talk about Sheroz and I don't care about the rest of the participants, I have imagined a boundary around him. So this is my choice. So he is my subject of discussion. Just like electron, yeah, you can have a boundary around electron. You don't care what is in the atom. So that is your choice. So it's a content. When we say a set, we have actually a boundary where you want to see these 3 markers, yeah, or these pencil as a collection isolated from the rest of the world in your mind. If you're not doing that, there is just a bunch of 3 pencils. And a bunch is only, maybe you don't even need the bunch. A bunch is needed to distinguish it from a set. Sometimes we use language to clarify our position that I don't want to see this as a set or as a multiset. Yeah, so maybe that can help. Okay. So yeah. So if we get back to that, how we define zero? Huh? Sorry? Define what? This thing? Zero? So now this equation has actually three things. It has that bunch, which is nothing basically, a bunch of nothing. Then I want to see them in a container, which in this notation is the multiset, an empty multiset. And because I don't want to write this every time, we'll call this zero. So when you say zero as a number, that will be different from nothing. Zero is not equal to nothing, because it is a new object built from nothing. And now maybe it's much easier if we move on. So let's say, how will you define one then? So instead of using a pencil or a marker or a chair, why don't we use this existing object? So now this tells me everything about one. I know this, like one pencil, one marker, yeah, one finger, yeah, one chair. This is telling me the same story. A collection with just one element, yeah. And this also reminds me that it's a collection, okay? Because if I remove this, then that zero itself is a collection. This is not empty. So what will be two then? No, remember, we had to, in sets we had to do this, yeah, remember? Why was this needed?
Because repetition was not allowed.
Repetition was not allowed, yeah? And that one itself, maybe that's the best answer. Repetition was not allowed. Because here it is allowed, so if I write here, so I can simply write two zeros. Simple. Two zeros. Because if I write one here, it has a problem. Why it is a problem? Because that has just one element. Here I was combining them. Yeah? I don't need it here. Okay? So I simply say it's much easier, and this will help us actually in counting, because when you have 0, 0, you can now count it. So these zeros will now play the role of those bars when you are counting 1, 2, 3, 4. This facility is not available in sets. Sets actually take you away from your day-to-day experiences. So what is the definition of 2? And it's up to you. This comma is, you can use a space, you can use a comma, you can use a semicolon. That doesn't matter, okay? What matters is that you see this. So now, just to make sure we understand the terminology, these two zeros without this container, it's a bunch of two zeros. But if I contain it, if I enclose it in that container, this is now a multiset or a bag or a box. You can even have a box in your mind. Yeah, you can use that as well. Some people use this box. Of course, not easy to type. Yeah. So just one last thing and then we are done, okay? So what will be 3? Okay, so now let's test that. How can this help us define addition? So that addition, which was very basic, the kid is now in grade 6, and we want to give him or her a more abstract, a more mathematical treatment of the subject so that things are precise now. So how will you define, for example, say 2 plus 3? Remember, I'm now using plus as a new symbol. This is how you see addition in your day-to-day life. Yeah. So first I will simply write this 0 0 plus.
You have accidentally put 4 zeros there.
Sorry, yeah. Right? And now you should know what you do when you add things. Yeah. You say add sugar, add some milk. Yeah. So literally, now we want to actually borrow from that day-to-day experience and define this addition accordingly. So what do? We just combine them. I will now have a new collection where I'll take these two from here. So it's literally combine. It's a 5. 1, 2, 3, 4, 5. So now we have a very clear definition of addition. And remember, this is not just symbols, okay? So normally when you are adding, let's say you are adding numbers without this concept. So what do? You have 2 fingers, and then you have 3 fingers, and then you say 1, 2, 3, 4, 5. You are using some physical thing, but you don't have a language, you forget that thing. So in your equation, you simply say, but this equation is not built from, you have this in your mind, but this now makes it explicit. The reason 2 plus 3 is 5 is made explicit by these steps, because your 2 and 3 are complicated things, and now you are unpacking it. Yeah, you are going from the collection to the bunch, and then you are actually, so it actually, now I'm telling you something very different, okay? Maybe this is easy to grasp, but this thing is kind of, so for example, we now know how do we combine numbers, how do we add numbers, yeah? But indirectly we are using an operation. For example, when you put a comma, think about a name for this now. So like you know the name, what is the name of this thing? A bunch, yeah? But how did we write that bunch? We put a zero, and in between we wrote a comma, or maybe you can have a space. So how about giving this operation a name? Yeah, just like we have a name for this, yeah? I took 2, I took 3, and then I had, so this plus is actually the name of an operation which we call addition. So how about giving a name to the operation which takes 2 objects and turns them into a bunch? Later on, you turn that bunch into a. So I'm actually now unpacking that process, which we skip. We straight away go to collections. Yeah. So I can simply say, just like this addition can be seen as, let's say it is a computer program or a function. Yeah. Let's say it's a machine which does the addition, and it asks you, oh, give me 2 numbers. What do? You give it 2 numbers as inputs. Yeah. If you have written any computer program, you write, okay, give me this input, and I'll give you in return the sum of these 2, and that is 5. So think about representing that same operation in this fashion. So what should I have in mind? I have a machine or a function or a computer program or an intelligent person. Oh, give me 2 things. So I'll give it. Or you can give it 2 and 3, doesn't matter. Okay? Because when you give it 2 and 3, you don't want them to add, okay? You want them to combine into a bunch. So maybe you can just write a comma there. Or maybe you can write a name, yeah, combine. What should be the output? A bunch of those two. And I have not yet turned it into a set or a multiset. So that is actually, why is that important? If you understand this concept, you can now say that, okay, when I'm adding two numbers, this is a more complicated thing. Behind the scene, I'm using this operation. So addition is, because addition operates at the level of containers. But you have to look inside the container, take those things out, and then put them next to each other. So that is literally what we are doing here. If we have things here, yeah, and things there, how do you add them? Let's say you want to add the contents of these two boxes. Yeah, let's put two there. Okay. So I have two pencils in one box, three pencils in another box. I hand it over to you. I say, okay, add it. What will you do? First, you will open it. So I'll take two pencils from there. It looks boring, but this will sink in your mind, okay? So now I don't have multisets, I don't have boxes anymore. I just have this bunch, a bunch of pencils and a bunch of markers. And how do I combine them? You can give this a name, yeah, combining, yeah. So now you know the physical detail behind addition. Addition is for more complicated objects, and behind the scene you are using these bunches. Okay, now after we have a clear picture of addition, do you want to see any few other examples to clarify this? So for example, as far as addition is concerned, how about 0 plus 0? Let's say you want to have 0 plus 0. What will be 0 plus 0? No, of course 0 plus 0 is 0, but we want to use this process if you want to understand this. So what will be 0 plus 0? This 0 is the empty box plus the empty box. And now we need to unpack. So an empty box, open it. Another empty box, open it. Combine them. There is nothing to combine. So this will also be an empty box. And that empty box is 0. So 0 plus 0 equals 0.
So you define 0 as nothing, right?
No, 0 is not nothing.
The empty box.
0 is the container with nothing in it.
With nothing in it.
Yeah.
And then you define 1 that contains one entity. That's 0.
That itself is 0. Yeah.
Yes.
But that is a box of nothing.
हाँ, लेकिन उसको आपने ऊपर ये डिफाइन किया कि वो खाली बॉक्स है.
हाँ बिल्कुल. लेकिन ये खाली नहीं है ना.
1 के अंदर वो वाली एंटिटी है और वो ऊपर आपने डिफाइन किया है.
बॉक्स है ना.
बॉक्स के अंदर बॉक्स है और वो वाला खाली है.
अंदर वाला खाली है, बाहर वाला खाली नहीं है. मैं आपको थोड़ी देर पहले एग्जांपल दिया था कि जब यूनिवर्स नथिंग से बन सकता है तो हम बॉक्स से बॉक्स नहीं बना सकते.
वो जो आपने एग्जांपल दी थी बैट वाली, जो आपने पाउच की एग्जांपल दी थी, उसमें जो अंदर वाला बॉक्स है वो फर्स्ट वाली एंट्री है, राइट? फर्स्ट वाली.
और ये बाहर वाला है.
यस. और जो उसके बाहर, यस, और जो अंदर वाला है वो फर्स्ट वाला है.
वो फर्स्ट वाला है.
यस.
So I think this was important, yeah, so that because we sometimes actually ignore these things, but they become important. Okay.
सर लेकिन देखिए 2 खाली बॉक्सेस हैं.
हाँ.
अब खाली बॉक्सेस 2 हैं.
ये यहाँ बात कर रहे हैं.
हाँ.
तो मेरे पास देखो ना, इसको ऐसे रख लेते हैं ना.
दोनों खाली बॉक्सेस हैं.
एक मिनट. ये भी खाली है, ये भी खाली है.
बिल्कुल.
तो चूंकि ये बॉक्स है तो ये भी 0 हो गया, और अब मैंने दोनों को ऐड करना है. तो what is the meaning of addition? Remember, एडिशन का मतलब ये है कि मैंने इनकी कंटेंट को ऐड करना है. आप ये ना कहें कि 2 बॉक्सेस है तो 0 plus 0 is equal to 2. That is not what is meant here.
हाँ.
Okay? Because plus is an operation defined for numbers, and numbers are collections. They are not the things in the directly. तो ये आपके जहन में होगा और ये डे टू डे में ये होता है जब आप कहते हैं ना कि टू फ्रेंड्स तो वो जो टू है आप उनको एज अ कलेक्शन देख रहे हैं you give them a name a pair you say couple pair so ये basically it is very much in line with what you क्योंकि mathematics is a language and the purpose of the language is to be as close to your day to day experience as possible. So that's what you expect a number to mean basically. ठीक है ना जब आप कहते हैं ना कि मतलब अभी 11 players they're actually playing maybe they are batting right now or bowling I don't know. So जब आप कहते हैं 11 तो 11 immediately should resonate that you are seeing them as a collection. ठीक है ना तो मतलब it's very much in line. So अब यहाँ पे कैच क्या है चलो सेट थ्योरी से तो बहुत बेहतर है ना लेकिन एक चीज अभी भी मिसिंग है बताएं जिसके लिए टॉप में मैंने एक चीज बताई थी ऑफ कोर्स वो सेट में भी नहीं है हाउ अबाउट नेगेटिव नंबर्स फॉर एग्जांपल यहाँ पे इसका मतलब है कि माइनस अच्छा अब माइनस का आइडिया कहाँ से आता है वी ऑल्सो नीड टू बी अवेयर ऑफ हाउ वी सी नेगेटिव क्योंकि ये तो एक नई चीज है ना तो नई चीज समझने का मतलब ये नहीं है so to learn something new doesn't mean that you forget everything you have already learned so we should now recall what do we mean by negative number and the negative number itself comes from
Negative integers.
no but that itself comes from subtraction
Yes, subtraction.
you need subtraction and so let me just give you a brief idea I'm now removing this. So our question now should be, what do I mean by negative 1, right? So negative 1, negative 2. Before that, I need to tell you, what do I mean by subtraction? Okay? So subtraction आपको पता है कि you just, for example, if I said 3 minus 2, what do? You have this in mind 3 fingers, yeah?
Yes.
And I remove 2 fingers. So 1, 2, I have 1 finger. So that's why you write 1.
Yes.
And we can do the same process here, yeah? We can now say, okay, it will be 0, 0, 0. And now I can now remove, yeah? So like instead of comma, I can say uncomma, yeah? So what do I get?
One.
Yeah.
One entity in the back.
Yeah, so now I have 1 entity, so that's 1. Now, what if I have 2 here and 3 there? So I will have 3 there and 2 there.
minus 1.
Yeah, I know that minus 1, but that minus 1 is, we actually remember that. We never thought about it. Okay, where does that minus 1 come from? So now it's the test. Try this. You can't do this. You cannot take 3 items
From
away from 2 items. So I actually tested this with my kids, okay? I had a little one and I gave them this problem. Tell me what is 2 minus 3. And you know what he told me? Maybe you ask this and you will see the same answer. He said 0. Because he said, his reasoning was that if I take 2 from it, I cannot take the third one, so it's 0. Because he had no concept of negative. So it means that mathematicians had to invent a new concept at this stage,
Yes.
right? So if you can say something about this, maybe you want to suggest something.
Like
Okay, so let me just tell you what they did. Okay, so what they did is this. Can I write this as 2 minus 2 minus 1?
Yes.
Yeah. So I can, instead of that, I'll say, right? So I do that process in 2 stages. First, I take 2 out, and then I take the third one out. So this will definitely give me 0, right? So what do I get there? And what do I get here?
Minus
0. Minus.
No, from these two you get an empty box, eh?
Yes, empty box.
And minus. So now you have a mapping, yeah?
Yeah, map.
There is only one thing you can do at this stage, because you got something new, you don't know how to do it. So give this a name. आप जब इसको नाम दे सकते हैं और इसको भी नाम दे सकते हैं, if you can give this a name, what is wrong with giving this a name? So this is what we put in by -1. That is the meaning of -1. Right? -1 means a new object. क्योंकि it's not a physical thing. अब मुझे नेगेटिव नहीं दिखा सकते. और बहुत सारे लोग ट्रिक लगाते हैं, डेबिट और you owe me or you owe me, or there is nothing physical basically. You're just playing games. Okay? So we have to agree that -1 is not a physical thing. It is not a physical collection. It is actually a name, a new name you give to something where you are stuck basically. वो बता दे
मे बी मैं रॉन्ग गलत हूँ शायद, लेकिन आयोटा द इमेजिनरी नंबर -1.
नहीं, वो तो स्क्वायर रूट है ना उसका. That's more complicated. Iota, that is a much more difficult problem than this. वो तो iota is equal to -1 and then the square root of it. Some people actually use that okay, iota is rotation. So they see iota as a rotation, and then you take another rotation and you get -1. But the problem is that you are now complicating things. You are going from one real line to the imaginary line, and then you have to talk about complex numbers, and I mean that is lost. Yeah, we need a very simple thing. Yeah. So so whenever you see -1, what should you keep in mind? You should see this as 0 -1. And it's not just 0 -1. Remember, so it's not just 0 -1, it is also 1 - 2. Because you can say, okay, why do you need a name? Why don't you simply write that? I mean, there is nothing you gain by just removing that. But the actual gain is, when you see this, that 1 - 2, here you also get stuck, yeah? Then, so there is an infinite number of calculations, all of them lead you 0 -1, and you need a name for 0 -1 because you don't want to write that 0 every time. It's an abstract thing. Okay, and we don't like this, because if we are using multisets, and if we claim that we are building something from nothing, we should use the same approach to define negative numbers in a similar fashion. So till the 20th century, this was not possible. This was the only way to look at negative numbers. But when the physicists discovered something in the 20th century, actually, let me hold that, and I'll give you 2 more examples. And maybe you can suggest that, okay, I don't need that 20th century discovery, okay? So now I'll ask you a few things, okay? Just to motivate, why should we still use the idea of bunches to talk about negative numbers, okay? Okay, so again, in order to follow this discussion, you have to remember that when you are writing symbols, mathematical symbols, you have a model in your mind, and that model is not necessarily the real thing, yeah? Because real things are much more complicated. So when I say, for example, you may be aware of, like, maybe I can give one example of acid and base. Yeah, you are used to that concept of pH. Yeah, when we say pH, what do you have in mind? What we have in mind, it's actually, it's a fancy way of talking about acidity, how acidic is something. Like your stomach is acidic, yeah? And for example, milk is not acidic. Milk is the opposite, it's basic, yeah? So when you drink milk, maybe it counters that thing. So let's say we remove all this detail, and whenever we look at a solution, that solution may have many complicated things, yeah? But we decide to care only about acidity and nothing else. Color, yeah, mass, I don't care. So there are only two things in my mind: acidic or basic.
Milk actually contains this.
Yeah, but these are details, yeah. I want you to remove the detail and you are bringing the detail. We don't want the details, okay? Milk has other things as well. Maybe उसमें मक्खी आ जाती है, फिर मक्खी को भी model करेंगे. So we need actually abstraction here. So if you only care about acidity and, yeah, the opposite of acidity. So what if you have the same amount of substance which is acidic and the same amount of subject which is, and you combine them, what will happen?
Neutralization.
Yeah, you will still have something, but as far as the thing you were interested in, that thing has gone. Remember, that thing has gone. Similarly, you can think about other reactions as well. Okay, another thing. You have money in your bank, in your pocket, and let's say you go and somebody comes and robs you. Yeah? So now you don't have that money anymore. So now the money is gone. Now you have zero, and let's say you had 100 rupees, and now you have zero, and you simply say, okay, 100 minus 100, yeah? Now this 100 is what you had in mind, what you had. Yeah? But here, you can now model everything that robber did to you, the physical things. So whatever he did can be modeled separately as a bunch. Yeah? So just like that pH, remember, pH is a number, okay? When you say pH is actually pH is equal to 3. आपको पता है ना कि when it is lower than 7, it means acidic. When it is higher than 7, it is basic. But that is only a number. The real thing is the acid itself. So instead of just saying 100 and minus 100, you should talk about the physical money and the robber, the actual robber. So you can now imagine, let's go back. So if you follow this discussion, I can now go back to that thing. Remember, how did we represent that combining things to turn them into a bunch? We just said a comma, yeah? So this comma, in general, will take one type of thing, let's call it A. A can be anything. It can be a number, it can be a collection, anything, yeah? And let's give it another type of thing. And what it does? It gives you a bunch of those two things, even if they are complicated. For example, even if this is 2 and 3, it gives you a bunch of 2 and 3. 2 and 3 themselves are collections, but you don't care. So now we can here introduce something. What if in order to model that situation, the acid base, the robber, yeah, whatever, yeah. Another thing, let's say I'm pulling something and you're pulling it from another side. That thing is not supposed to move because there are two. So you say zero force, but physically there are two things acting, yeah. Just like this thing is now not falling down, yeah. So you say zero force, but actually there are two forces, the gravity and the reaction force. So I want to actually get into that. I don't want to ignore that. Yeah. So what if it is that thing and what is the thing which is anti of that? Yeah. So just give it some name. Just call it a bar. Yeah. So like if this is acid, this is base. If this is force pulling, this is pulling from the other side. You can now imagine an anti of everything. So what will this do? No, zero na kahe na. Nothing. Because zero is not nothing. So basically you have no bunch. Nothing. They just disappeared, both. The box bhi nahi hai na. Box to hum kar rahe hain. Box to baad mein aata hai na. It is nothing basically. So of course, वहाँ पे तो वो आपको neutral solution मिल जाता है because that is not my concern. My concern is the acidity. So as far as acidity, so if I had a pure thing which only represented, so now get back to that 20th century discovery. antimatter. That's exactly what it does. So if you have an electron
Positron.
and then a positron, combine them, and I don't want to write plus. Many people say plus, that's a problem because plus is for numbers. These are not numbers, they are things. Okay? So maybe, I mean, if you say what I mean by plus, that's fine. Yeah. If you say, okay, by plus I mean this, then it's okay. But if by plus you mean addition of numbers, then this is wrong. Okay. So if I now combine these two, what do I get? There, in the physical experiment, the matter is gone, you get 2 photons. But you're not interested in photon, you're only interested in matter. The matter is gone. Yeah. So now we can say that for every object, we will have an anti-object. Even though this is abstract, but we know this has a relationship to the physical world. Be it a rubber, be it an opposing force, be it an antiparticle, yeah, anything, you can imagine it. So now, with this understanding, let's say we do something. What is this? This is 1, yeah? 1, yeah. Because otherwise we will call it 1, yeah? So just above that, I'll just write 1. Just write the anti of it. So what will I write there?
-1.
Actually, we don't want to jump to conclusion. No, we want to deal with bunches. Yeah, this is because without this is that 0, and this is an empty 0, and I want to add the 2. So do not use anything from numbers, yeah, because we want to build it from this. So what is our method of doing these things? We just open the box, combine the 2. So what do I get? 0. And now it is so now this should tell me that I don't have a name for this set, yeah? But I do know that I got, but I know I have the physical thing. So I can define -1 here. Now this is a different definition from there. There I was just playing with words, but here it's an actual thing. So now we have a name. So 1 is actually 0 contained in a multiset, and -1 is an anti-0 contained in a multiset. So -1 is now connected with a physical object. In the same way, 1 is connected to 0. Of course, I should not call it physical. It's still abstract, but the abstraction, जैसे कहते हैं, there is a method to madness. अक्सर हम कहते हैं ना. So abstraction भी ऐसी होनी चाहिए जो real world के साथ connected हो. Abstraction का मतलब ये नहीं है कि आप कुछ भी कहते हैं. So it is a very careful abstraction which is connected to the real world. Okay. So now we have so now you can imagine. So how will I then define, for example, just recall, what was 2? Right? So what will be -2? 2 anti-zeros. No hanky-panky. Okay? And same goes with -3 and so on. And now we get back to subtraction. Because now we have the tool to perform our subtraction without giving any new name. So we also, we did give a name, but we gave a name to the bunch. Yeah? And this was a label. So if you are against this, then you should be against this as well. Yeah? Agar ye allowed hai, to ye bhi allowed hai. So there is no problem. There we had a problem because we were giving a name to 0 - 1 without any, I would say, connection to the bunch. So let's subtract, okay? So now we get back to that problem, 2 - 3. So what do we do? What is the first thing we need to do?
Representation of 2?
No, before that we need to do something.
Yes, yes.
So because the fundamental operation is addition basically. Yeah. So actually we have turned it upside down. There, the fundamental operation was subtraction, and we used subtraction to define negative numbers. Remember, how did we define -1 there? You use subtraction to define negative number. We are doing the opposite here. Why? Because we have a direct connection for the negative things. So subtraction is an addition where the thing subtracted, क्योंकि ये भी तो है ना, subtraction का क्या मतलब है कि वो rubber वाली analogy आप ध्यान में रखिए ना, कि this -3 का मतलब ये है कि there are actually a robber with 3 hands and okay, he takes 3 notes from you, yeah. So अब क्या हो जाएगा? 0 0 plus right? Now you open the box and combine all of them because you are still using comma, yeah? So 0 0. Now tell me what? This 0 bar will cancel this 0 bar. Now this is a different type of cancellation. This is not about the minus. This is when, just like the acid base, yeah, the forces. Now these are physical things. Matter, antimatter, yeah. So right? So I'm left with one anti-zero. And that is -1. So we have actually placed subtraction on the same footing as addition. They're both as, so I mean, they're both as abstract as real. Jitna addition abstract hai, utna hi subtraction bhi abstract hai. Jitna addition close to reality hai, utna hi subtraction close to it. We don't need a new layer of abstraction. And none of this would have been possible with sets, of course, because sets, that's a no-go. वो तो addition के लिए भी appropriate नहीं था. Subtraction को तो भूल जाया.
Multiplication.
हाँ, multiplication, right. So there are actually two. So because that is a more advanced topic, so I would like, if there are any confusions, because we are basically done. We have negative numbers, then we have addition, we have subtraction. Because there are two ways to deal with multiplication. So if there are any questions about addition, subtraction, negative numbers, we should ask it right now. I think, yeah, it's clear. So let's deal with subtraction, with multiplication, right? So again, in order to follow this discussion, you need to again recall what you mean by multiplication. Yeah?
Multiplication is successive addition.
Yeah, and remember, do you want to say something? Okay. So just give an example. Of course, we are now dealing with the with integers only, right? Fractions or real numbers, pi वो नहीं है, वो next lecture के लिए कर देते हैं. So for example, what do we mean by 2 times 3? There are two ways of looking at it, right? You either say add 3 2 times, yeah? So you will say, or, and they should both give you 6. This is one way of dealing with it, okay? So if you are happy with this, then we don't need to do anything else. Why? Because we know it uses addition, and we have a sound mechanism for addition. So you can, at this point, you can get down to those details, 3 0 0 0. If that is acceptable, then we don't need to have a separate mechanism for this. because multiplication is built on addition. Yeah, but maybe you want to go far and you say, okay, just like we did it for multiplication, we want a similar mechanism for multiplication as well. That is more complicated, but just suggest me whether that is needed or not.
Yeah, it's not needed.
It's not needed, yeah. Maybe later on we will see that it is needed. As far as this example is concerned, remember these are both positives. Maybe that's why we don't need it. Okay. So now, how about negative 2 times 3? So here we had a choice. Yeah. We either write 3 plus 3 or 2 plus 2 plus 2. Here, choice. We can only write this in one way.
Yes, negative 2, negative 2.
Negative 2 plus negative 2. क्योंकि जो repeated addition है वो सिर्फ यहाँ पे आपको नजर आएगा, उधर नहीं आएगा. Okay, you don't have a negative repeated. So yeah, you are fine here as well, right? Now what about this one? Actually, it's easier. So here you had to flip it in your mind. Okay. So now so these are easy. Okay. So now the tricky one. You cannot use any of those tricks here. Of course, don't tell me, oh, my negative times negative is plus 1 because I saw it. That's not a justification. The reasoning you can give in these 3 examples is not available here. Yeah, I'm sorry. You have to actually, so many people say, oh, just define it. And that iota thing, yeah. But that actually you are creating. That is actually similar to, let's say you see a word while reading a document and you don't know the meaning and you see dictionary, and in the dictionary the meaning uses another word which is even more difficult. And then you have to find another dictionary, and then you keep looking at those words. So we need a simple explanation, okay? So anyone who can remember this? How the math guys dealt? Okay. So this was actually solved by, just like an addition. So we have basically 2 operations, yeah? Addition and multiplication. An addition, we have a concept of 0. 0 is important for addition because it is the additive inverse. Yeah. So if you add 2 things, yeah. For example, if you have A and if you have negative A, you get 0, right? So let's not discuss this thing. Yeah. Similarly, you have a multiplication of inverse as well. For example, if you have A and you have 1 by A, or you just call it A inverse, you get 1. Yeah. So these concepts are foundational. Okay, so let's use this one. Okay. Now, before this, we want to deal with negative 1, right? So I just write 1 here and negative 1 here. What do I get? 0. And you should see this not just because 1 minus 1 is 0, but see this as 1 and minus 1 being the additive inverses, and 0 is the additive identity. Because addition is commutative, you can also write this in this way. Right? Okay. So now tell me, because you don't know what this means, yeah? So forget about it. Let's say you don't agree with that definition, minus 1 times minus 1 is plus 1. So let's say, okay, see this as a number, right? Okay? So can I write this as negative minus 1? Yeah, because putting a negative sign is the same as multiplying it by minus 1, right? So if I now look at this thing, negative minus 1, and if I hide this from you and I just call it A, so can I write minus A? Right? So what is its additive inverse to get a 0? Right? Now you put that back. So what do you get? Minus plus
Minus 1. Minus 1.
right, let me just check. So minus 1. Okay, so to get a 0, I need A, and A is actually minus 1, right? So far, so good. But here you know that the additive inverse of minus 1 is plus 1. So this must be plus 1. You define negative times negative equals positive, not because you have a justification for it, but it is a requirement for this rule, which is foundational. Imagine you don't have this rule, then all the algebra, all the arithmetic goes down into dustbin. So certain things have to be defined not because they can be justified directly, but because they are requirements for other things. Yeah. So if you are happy with this justification, then basically we don't need anything. Yeah. But let's say you don't agree with this. Okay, you can say, okay, you just manipulated things, and you do not have a direct justification, and you use. Of course, that is also something which is cannot be denied. Yeah, you would never want that rule to be violated, right? So, what if we try to define multiplication directly? So there are two ways. Either we do that, or we just take more questions, because if we are running out of time. Because I don't think that is so, I mean, it will open up some new things, but maybe it will actually raise new questions. So if you think this is enough, we should just take questions. So maybe we can have a voting. Should we try that for multiplication, or we're just happy with this? How about, what do you suggest?
Yeah, it's up to administration.
बस ठीक है actually it actually brings something which is not pleasant, so I'll tell you that in advance. And but before that, I'll give you my justification for that. Okay, so one thing is that we know quantum mechanics. Okay, so when you go down to the quantum level, things happen which you never expect. Yeah, an electron behaves as a particle as well as a wave. Yeah. And many things actually are violated. So here you will also see something like that. Yeah, be prepared for that. One thing. The other is something called the modular arithmetic.
Yes.
Yeah. For example, when do you have a clock here? Yeah, there. Okay. So when you go to 12, and when you add 1 to it, 12 plus 1, you don't write 13. Yeah? Of course, you will write 13 in a 24-hour clock. But in a 12-hour clock, you just write 1. And in a 24-hour clock, 24 plus 1 will be 1. It will not be 25. Yeah. So that is also something that if you want to limit your set of symbols, yeah, finite number, then when you reach the end, you just repeat. Yeah. That's what we do every time. Okay. So keep these two justifications in mind: the modular arithmetic and the quantum things going actually wild. So let's try this now. So let's say I want to multiply 2 by 3. So I say, okay, 0, 0, plus 0, 0, 0. So maybe if you have seen Japanese way of multiplication, they just draw lines. So they will draw 2 lines, and then they will draw 3 lines, and then they will count the intersections. So physically you are actually replicating, yeah? Because, and what does the intersection mean? That these 2 lines, yeah? And then these 2 lines, so you are basically having a mesh where you replicate things. So we can do something similar here, okay? What we can say is that each of these zeros has to be combined with each of those zeros. So if I start with this 0, you can combine it with all of those 3, and you can use addition. So you will say 0 plus, maybe we can, yeah. So I will say this 0, starting with this 0. So this 0 plus this 0, 0 plus 0, right? Then this 0 plus that 0, and then plus. So I'm now done with the first part. Just like those lines, yeah? Remember, if you just focus on one line and you see at how many points it intersects with the other. Now you do the same here, so what will you do? Now 0 plus 0, we have seen before, 0 plus 0 is 0, yeah? And you can show it with that opening up, and yeah. So what do you have at the end? Two times 3 is equal to 6. So you have a direct connection if you use addition to represent that, that actually, because repeated addition, yeah, multiplication is repeated addition. So you are using actually, this is repeated addition in a way. So this is fine, okay? But now we have a problem. We had no problem saying 0 plus 0 is equal to 0, yeah? But let's say one times 0. So we will have 2 things which will lead to conclusions. The conclusions will be okay. Have you heard of that thing from Shakespeare? I think he said something that even if you cannot, that can be given as a justification for the earlier argument, negative times negative should be positive. So Shakespeare, I think, once said that if you eliminate the impossible, let's say you have 4 choices in an exam, MCQs, and you are definitely sure that these 3 are wrong. The 4th one must be correct, even if you don't know, even if you don't understand it. So if you eliminate the impossible, what remains must be true, regardless of how improbable. So that is the foundation we will be using it. Okay, you will see something which will be disturbing, but that must be true because we will be using reasoning which is sound. So how will you go about it? Yeah, one is 0 content in a container times so what will you do here? When you had something you could add, yeah, but 0 plus nothing, that's not defined. So what is the trick you have to use? But before that, before we try this, I want you to tell me the answer because you know the answer. Because we are only exploring the mechanism. What should be the answer?
Empty box.
No, forget about this. 1 times 0 is, you know it should be 0, yeah? So that is something without any question, okay? Because if 1 times 0 is not 0, then we should stop this debate, okay? So now let's deal with this. I can do one trick here. I can recall my friend anti-0. So empty box can be written as 0, comma, anti-0. I know they cancel each other, right? Is this clear? Yeah? And now I can do the trick. 0 plus 0 and 0 plus 0 plus 0, 0 plus empty 0. 0 plus 0 I know is 0, okay? But I cannot say anything about 0 plus, because it's a new thing. I have not defined addition for 0 and anti-0. So just write it down as it is. And I will not try this directly because I do not have any reasoning. But I know this is 0. Shakespeare, yeah? So now tell me what this must be. You can tell me. What should I write next to 0 to make it an empty box? Because I need an empty box basically. Yeah, so this must be an anti-0. So now we discovered a rule. Actually, this rule is not so disturbing, yeah? So what we discovered from here? That 0 plus anti-0 must be? No, no. No, this is empty, but this is only empty if this is anti-0, because only an anti-0 can annihilate a 0. It's literally destroying the 0. So this thing must be anti-0. And this conclusion was derived from the requirement, yeah, okay? And this is not so disturbing. Why? Because you know 0 plus anything is that thing. So that is not a problem. The problem comes later with the new one. What is 0 times 0? Yeah, so first I write down the answer so that Shakespeare is actually reminded. And now we do this. And now be ready for something unusual. What is 0? Empty box, right? This is 0, empty box. And I don't know how to deal with nothing and nothing. So I again recall my friend. 0. So this is the same as 0, anti-0, because they cancel each other. And cancel doesn't mean addition, but literally destruction. Yeah? Plus, times, right? So now let me remove that, because we are done with that. I'll just leave this part because this was a conclusion. And now start from here to there. So can you help me complete this now? 0 plus 0? Then 0 plus? 0 plus anti-0. 0, anti-0 plus 0? And anti-0 plus? Now we'll do what we can and leave what we can't. So 0 plus 0? 0. 0 plus anti-0, we just discovered it. This? Okay? And that, I cannot do anything, so I have to just write it down. Okay. And I know the answer has to be 0. These two cancel, right? So I can just remove it, yeah? So anti-0 has to be cancelled by something to give me 0. That thing must be. Now this is disturbing, right? Two anti-zeros addition, 0. But don't get disturbed, because we know what we are doing is correct. And that quantum mechanical thing, but my favorite is the clock arithmetic. So if 24 plus 1 is not 25 but 1, actually you run out of symbols, yeah? Basically you, just like, you know, why did you, for example, if you look at the 12 clock, how many symbols do you have? 1, 2, up to 12. So when you say 12 plus 1, you run out of symbols, you go back. Okay? So here you have a set with just 2 symbols in this debate. 0, you just have 2 symbols, just like 1 up to 12. So 0 plus 0, 0, you are in the set. 0 plus anti-0, you are again in the set. You are not yet exhausted. But anti-0 plus anti-0, you cannot say 2 times because that is outside. So you have to go back. Of course, that's not convincing, but that's the price you have to pay if you want it to get. And if we have a theory for addition, and if multiplication is built on top of addition, we should not bother, actually. So, but it's still an interesting exercise.
How would you do division?
Division is not a problem. You know, remember the fundamental operations are only two: addition and not subtraction. Addition and multiplication. Because subtraction is just the opposite of addition. You know, why was that so important? Why is this so important? This reminds you that subtraction is just the opposite of addition, yeah? Because this can be seen as A minus A. So what you call division is just the opposite of multiplication. So it's not a new operation. Okay. So that was it. So I hope I just repeat the goals of this lecture. The goals of this lecture were to define numbers, both positive and negative, integers, yeah, because we are not into more complicated numbers like fractions or real numbers or complex numbers, on a footing which is very foundational. And people have tried that to base it on set theory, but set theory collapses. Set theory is important for in its own right. Yeah, it has many applications. But as far as counting, addition, subtraction is concerned, multisets are the right objects. Unfortunately, they're not taught at school level. So my request to the academia, and especially those who are planning curriculum for schools, they should introduce multisets. I'm even willing to give seminars or write, for example, a tutorial or whatever, but only if I know that people want to actually embrace this idea. So that was from my side. Thank you.